Okay, we can get started. It's a great pleasure to have Professor Ye to visit us for the next week, starting from today until 27th. I think Professor Ye has been working on many aspects of conventional matter systems, including both strongly correlated and weakly correlated systems. And today, his talk is about the bridge, the marriage between them. Let's welcome.
Yes. Also, I would like to thank Professor Zhou Liujun to invite me to be here in the very nice city and country, and also it's my first time to be here and very excited. Here, very nice place. And today I want to talk about this my recent work about this Fracton topology orders with boundary Toeplitz braiding. It's kind of a marriage between strongly correlated topological fields and weakly correlated topological physics. I will explain this bunch of terminology later, and in fact, actually, you can forget about all this terminology. Just remember that we are dealing with strongly correlated topological phase matter, and the mathematical tool comes from the free Fermion topological instrument. This is our key message. Okay, I'm Peng Ye from School of Physics, Sun Yat-sen University in Guangzhou, China. Okay. Yeah. Okay. This is my collaborators, and Li Boxi is my PhD students currently in the fourth grade, and the boundary of third and fourth grade. And the second collaborator is Dr. Zhou Yao. He was my former postdoc in Sun Yat-sen University. He's currently a postdoc at University of Hong Kong. The signal. Okay, let me start with the story about the Fracton topology order from this. Recording.
I forgot to share the screen.
Should I restart?
Have
you okay?
I don't think that's necessary.
Where should I start?
Maybe you can just continue.
Okay. Okay. Let me start with the story of a topological order from this story of a fractional corner Hall effect in 1980s, when I was born, 1980s. So the fractional corner Hall effect is very famous, strongly correlated physical phenomenon, which was ever won the Nobel Prize. And here's the very important progress of this fractional corner Hall effect is that Bob Lockley proposed this very famous locking wave function for this very complicated states method. This is a very non-trivial approach to this matter physics, because conventionally we want to use standard perturbation theory to this Hamiltonian instead of wave function. And here people for the first time propose this tri-wave function to try to understand this matter, rather than solving this complicated Hamiltonians. Okay, the very peculiar feature of this wave function is that the power of this polynomial is 3. This number 3 comes from this the factor that this fitting fraction is 1/3. Okay, fitting fraction 1/3 for this lowest lambda level. Okay, in addition to this wave function, people also use alternative approach to study the fractional corner Hall effect, or we can call it as topological order in 2D. The approach is so-called hydrodynamic field theory, or we can call it as some kind of 2+1D TQFT topological quantum field theory. In 2+1D, we use this Chern sum theory, which is is kind of a T equal T in 2+1D space-time to describe this the ground state of this fractional Hall liquid. And here we can find that this the Chen-Sum theory is written in this form. The coefficient 3 is quantized to integer, and this quantization of this prefactor is guaranteed by this large gauge transformation. We don't need any symmetry to protect this quantization of 3. That's very important. So in that sense, we don't need any symmetry to protect the topology order, the topology order. Okay, so here from this TQT, we can compute this very famous topological invariant so-called ground state dynamicity GSD, which is only dependent on this genus of this manifold, where we put this Chen-Sum theory on. And this, for example, for the first torus, the G is not like 1, so the GSD is 3 for this Chen-Sum theory. And in addition to this GSD, we can also have this compute this number of super selection sector, or likely we can call it how many distinct topological excitation in this +1D theory. And also based on this three distinct distinct anions, we can compute this fractional charge carried by each anion. And then we can compute this data, so-called braiding statistic, braiding phase. We can move one particle around another, and then the wave function will decouple AB phase. This AB phase can also compute from this Chen-Sum theory in principle, and also we can design this so-called fusion process to study this relation between different anions. Okay, so in addition to this data, if we put this theory on the open manifold with a boundary, we can deduce this boundary chiral theory, which can be deduced based on this so-called light cone gauge and open boundary condition. This is very standard result constructed many years ago. Okay, yes, it's not simple. I cannot change it. No. Okay. 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 In addition to this single component Chen-Sum theory, we can also have so-called multi-component Chen-Sum theory. We believe that this multi-component abelian Chen-Sum theory can describe all abelian topology order in 2+1D. This is the formula of this multi-component Chen-Sum theory. Also, in the literature, we alternatively call it as K-matrix Chen-Sum theory, because this coefficient single number 3 now is changed to this symmetric integer K matrix Kij. Kij is symmetric and an integer value, which is quantized by this condition of a large gauge transformation. And the second term is a quasi-particle term. Here, the integer vector L label the quasi-particle, and it's Q label this charge carried by each layer of this topological current. So this capital A is external EM3 to prove this charge fractionation. And based on this theory, we can also compute the GSD for this kind of topology order on this any manifold, and also we can compute this mutual statistic between different anions labeled by L and L prime respectively. And this theta characterizes this mutual statistic between L and L prime. This is very important data I will use later on, and here I use this square to highlight the result. Another topology data is so-called self-statistic, also we call it topology spin. We can use this formula to compute this topological spin. And in addition to this data, we can also compute the fractional charge. Use this formula. The take-home message is that in principle we can use this Kij, L, and Q, this function of data, to compute almost all interesting topological data for all abelian topology order in 2+1D. And also there's a central charge, a chiral central charge, which is defined as the difference between this the number of positive eigenvalues of K and the number of negative eigenvalues of K. Okay, this is very standard result. Okay, and here is some example. So for example, the simplest one is K equals 3, which describes this chiral looping state with fitting fraction 1/3. And also this is nothing but stacking of a two-layer looping states. And this K describe this the low energy physics of this very famous torical model. Also, we can call it Z2 topology order. And these two K are equivalent to each other because we can use this general linear transformation to transform one K matrix to another. These two K both describe the so-called twisted Z2 topology order. Also, we can call it double semi topology order in 2D. This is some topology.
This multi-component CS theory described fermionic.
Yes. As long as you have at least one entry along the cycle is odd. For example, this looping state is nothing but very simple fermionic theory.
Your previous page mentioned that in that C central charge, I think you mentioned the C equals a positive eigenvalue minus negative.
Yes.
That means C must be an integer.
Yeah, you're right. C integer. So here is abelian topology order. Non-abelian topology order, chiral central charge is always integer. So for non-abelian, you can have chance to have the fractional.
So that means that even for fermions, the central charge is still integers.
And as long as this theory is abelian, for fermion theory, you can also have abelian or non-abelian. For abelian theory, no matter if it's bosonic or fermionic, the chiral central charge is always integer. Yeah. So let me try to change page manually. Okay. So now the question is, can we apply this Chen-Simon theory, not computer science, Chen-Simon theory to 3D? 3+1 is real space, 3D. Consumer theorists interchangeably use 3D and 4D. You just be careful. So can we apply the Chen-Simon theory to 3D topology physics? Because we are new generation of topology order fan. We have to survive to do something beyond 2D. So we want to do some higher dimensional, maybe 3D or 4D, 5D, right? So here we want to ask this question: can we apply the Chen-Simon to 3D? Of course, we cannot, because this space-time integration is 2+1D. So we cannot direct use this theory to describe 3D theory, 3+1D theory. Because intrinsic 3+1D TQT is a so-called BF theory. This theory is simplest TQT in 3+1D. Here the B is two-form U1 gauge field. So here T carry two Lorentz indices. So here's 1, 2, 3, 4. So 4 forms. We use this 4-form anti-symmetric tensor to contract all the mu lambda room together. Then we end up with a scalar action scalar. So here's the BF theory, and based on this BF theory, we can compute this particle loop braiding, which is nothing but edge phase. You can regard this, for example, when n equals 2, you can regard this process as some process in superconductor. So So you can have electron move around some pi flux. Then the ground state will end up the phase -1. So it's so-called part loop braiding. And in addition to part loop braiding, we can also have some twisted version by add additional topological terms, the AADA term, A1, A2, DA2, or A2, A1, DA1, or A1, A2, DA3. And as long as you have full form widespread that, this is very simplest generalization of BF theory for twisted BF theory. And also, we can also have some AAD term. Once we add AAD term, we can have much more complicated braiding process, such as 3-loop and BR braiding or loop braiding. So I have a lot of time, and I don't have time to describe detail here. But if you are interested, you can read this two paper, the original paper. So here, okay. So here, so then we still try to apply this transition theory to describe the 3D phase, and there is still a chance. And the chance that we regard this ij indices as a coordinate along z direction, right? So now this a mu I x y t, this field becomes a mu x y I t. So this indices I now becomes the coordinate the z direction. So now the simplest the simple example is this trivial stacking was this 1/3 Lofting state. So now although the formally we still have this action, this D3x, but now this ij we need to reinterpret this ij as the coordinate along z direction. So now it's intrinsically the 3+1D theory, right? 3+1D theory. In fact, this line of thinking coming from this construction of the quasi 3D fractional quantum Hall effect many years ago, maybe in this famous paper by Michael Levin and Fisher in this field, as far as I know. And recently, people reuse this line of thinking to study this so-called 3D Fracton topology. I need to explain what is a Fracton and what is a 3D Fracton topology. Okay.
So now that we have the BF theory as T2FT, why do you still want to apply T7 to 3D? And what is the original expectation?
You mean?
Yeah, now that we already have T2FT theory.
Yes.
3D.
Yeah.
Then why do you still want?
Yeah. I need to explain later. So basically, I want to use this transition theory to describe some 3D topology called Fracton topology. For example, for this K matrix, if we reinterpret ij as this coordinate along this z direction, the stacking direction, then you can find that the quasi-particle of each layer cannot correlate to each other. So in this way, we can say that this area now the quasi-particle have some restricted mobility. They can only move in some subspace. So this is our starting motivation to try to construct the 3D topology with quasi-particle that have some completely or partially restricted mobility. So this is our motivation to here. Okay, so let me show one slide to give a quick review about this so-called Fracton physics. So here are the two lines. The first line is we can regard this Fracton as topological citation. So-called in this so-called Fracton topological. Here's some typo here. So here, Fracton in general sense can be regarded as quasi-particles that cannot freely move. They can only move only in some subdimensional space, subspace. So for example, here is the model. Here is so-called 3D model. We can have this Fracton labeled by this minus eigenvalue of this cube term, AC term. AC term is formed by 12 poly X here. So this quasi-particle cannot be moved freely. You don't have some bendable and deformable string operator to move this particle to another place. So here we see we call such particle such a topological quasi-particle as fractons. The second line is we can regard this fracton as some constituent particle in some many-body system that conserve high moments. So there are many properties here. I don't have time to describe the detail about this line. If you have some interest, you can read this paper. Okay, so let's go back to look at our idea to regard this K-metric transform theory as some 3D 3+1D TQFT. So here we consider some more general way this K-metric rather than this K. This K is too simple, right? So here we consider this K matrix. So here this A is 2x2 matrix and B is also 2x2 matrix. So here this K is a translational environment along each diagonal line, right? So this K is nothing but a tridiagonal Toeplitz matrix here. So before we add this B matrix, this A describes this ZM topology order for each layer, and then on top of that, we add this B matrix. This B matrix describes the intercoupling without breaking translation symmetry along Z direction. And there is very important point that this B is local. So here we only need to add this local interaction between this layer. So we don't need to add this non-local topological coupling here. So we start with this K matrix, try to understand the boundary effect. So naively, we have this two very different boundary, the so-called XY boundary and this Z boundary. And on this XY boundary, we expect that there is some high-order form liquid, which is very standard, right? So now our question is that are there any non-trivial phenomena on this Z boundary, upper boundary, and the lower boundary? This is new boundary, right? This is new boundary and have not yet been studied before. Okay, so here before we talking about this context of transform theory, once we have this K matrix, we quickly remember that the existence of a Toeplitz matrix reminds us of this very famous topological insulator and topological superconductor.
Sorry, what is N even?
Which one?
And not that little N, but which is A.
You mean as top N?
No, little N.
Little N. Here we study as N is given, and you can also study N is odd. So here we, I remember my example always N is given. I want to try to avoid formula. Formula is complicated. So, okay. So here, yeah.
So is the boundary condition of Z boundary unique?
Open. I use open boundary. Once you want to study whether or not the bulk is gap or gap is, you can use this pure boundary condition by some additional term here, this lower left and upper right. And here we only study as an open boundary because we want to try to understand what are this and non-trivial phenomena on the Z boundary. So we just use this very simple open boundary condition. Use this K matrix. Okay. Now, the existence of this kind of vector reminds us this very famous TTI and TSI, TSC. This is very famous 10 years ago, more than 10 years ago. It's a very very developed area field. Okay, so here we found that we have this once we have this K matrix as Hamiltonian of this topological newspaper, the question we want to ask is, are there some non-trivial boundary Z-mode or garbage state on the boundary that are protected by some symmetry? This is very famous story. So this temporal wave classification of the topological newspaper and topological supercomputer this famous result. And now, because of this similarity of the mathematical structure, we want to ask, once we have this boundary Z-mode on this K matrix, are there some non-trivial results in my context, right? In my context, this is our motivation. This is our motivation. So basically, if K matrix is a free-forming Hamiltonian matrix formally, but remember that now we have to enforce the condition that all entry of this K matrix must be integer because we need to guarantee this large gauge transformation. No, right? And this is only difference here. What happens if K matrix have zero modes on the Z function? So
by having zero modes, you mean it has some eigenvalue being zero?
Yeah, you're right. On the boundary.
On the boundary, what does it mean to be on the boundary?
I mean this eigenstate on the boundary. Eigenstate. H-state. Yeah. So our key finding, take-home message is a so-called Toeplitz braiding. I create the name. You can just figure out the strange name. Yes. Okay. So the result is that once we have the boundary Z-mode of the K and some additional minor condition, this minor is non-integer upper right and lower left elements of K inverse, because in some very rare case, there are some you must avoid the real case because this braiding phase may be 2 pi. 2 pi is 0. 2 pi is 0. We must avoid this very real case. The main necessary condition is boundary Z-mode of K. Then we combine these two conditions together. We have so-called Toeplitz braiding. So what is Toeplitz braiding? Then we define this braiding process as following. This braiding phase angle, theta between the upper area and the lower area are always oscillating, not converge to 0 more 2 pi. Even though this the size is thermodynamically large. Here we must remember that the system size along x and y already at the thermodynamic limit, because we use Chen-Sam theory to describe each layer. So this xy direction already in the thermodynamic limit. But along z direction, we still starting because this K matrix, we start with finite dimension of K matrix. So our starting point is finite dimension along z direction. Okay, this pointer has no power. Okay.
Oh, sorry, what is this braiding name?
Yeah. I have a teacher here. Once you braid this upper area, as long as the projection will a lower area on the upper boundary are exactly inside this circle. then this upper area will pick up phase. Will pick up phase. Now, because then we can imagine that this braiding process happens in different universe, parallel universe. So it's very strange. It's very strange braiding process, and there is some connection, some talk, communication between two very far away parallel universe. So this is very strange braiding process.
Oh, so it means that if two ends are getting braided on the upper boundary
and lower.
and the lower.
Yeah. So you can basically you can fix one and braid another, as long as the lower area is projection exactly inside this circle for upper area. Then you have this space. And what I want to claim is that as long as the K matrix has boundary symbol, and we as well as some additional minor condition, then we end up with the concluding that this braiding phase angle always oscillating, not converge to 0 or 2 pi, even though the size along z direction is in thermodynamical large. Okay. This is a definition of Toeplitz braiding because we use this feature of properties of Toeplitz matrices.
There's one more question.
Yeah. Oh, yeah.
So what's the difference between Toeplitz braiding and the conventional braiding statistics?
I already explained that basically conventional braiding that two area in general must be in the same universe, same 2+1. Same 2+1. For example, here is the area, here's the other area, you braid one area around another. We pick up the phase. But now these two areas are in different 2+1 space time. They are separated by a very large distance along the z direction, actual dimension. So this way we call it Toeplitz braiding, the new kind of braiding. Okay. So here, just take a simple example. This is a very simple free-form topological illustrated in 1+1D. It's very simple Hamiltonian. So here is forget about this k. You can write hand h here. You are comfortable, right? So here is a b. So here is k is a symmetric Hamiltonian, real symmetric Hamiltonian. So Hamiltonian is Hermitian. This so-called Hamiltonian is Hermitian, and this Hamiltonian has two phases: trivial phase, non-trivial phase. In the non-trivial phase, we have this boundary mode, right? It's a topological incident protected by chiral symmetry. And if I remember correctly, I don't know what is chiral symmetry. It's very complicated definition of chiral symmetry. So here is A and B. For A is M and B is L, right? So here we find that for this example is very simple, and we can analytically compute K inverse. K inverse can be analytically computed based on this paper, and we can analytically compute K inverse. Very important result. And we found that if you want to have this non-trivial braiding between upper area and lower area, at least we have non-zero lower left and upper right elements of this K inverse, right? Lower left and upper right K inverse. So here we find that when absolute value n is larger than L, then this state is trivial state. We know that. And we also find the theta upper this theta angle exponential data to 0, right? The exponential data. But if we choose the parameter region like m is this n is smaller than L, then this topological incident in 1D is topologically non-trivial as a boundary symbol. Then this lower left and upper right. Here, if we compute this braiding phase between upper angle and lower angle, we need to use this lower left element for upper right element because it's symmetric. You just using the lower left is enough. So we found that in this boundary region, this step before we mod 2 pi, this it has permanent not, right? So then once you mod 2 pi, this theta actually is permanently oscillating in this first Brownian zone, right? In first Brownian zone, because theta is defined mod 2 pi, right? Defined mod 2 pi. So in this broad region, we in fact have some non-trivial Toeplitz braiding between upper angle and lower angle. But here we have some additional minor conditioning to avoid this 2 pi over 2 pi phase, because 2 pi, 4 pi, 6 pi all are equal to 0. So we must avoid this minor cases, real cases. Okay, this is condition. So here we plot this numerical result. Numerical simply work that we find once we have the trivial topological system, which means that we don't have boundary zone mode. For example, and when M is 2, here L is 1, we find that's theta. When we increase this system size, we find that the theta rapidly come to 0, right? So here, once we have non-trivial topological system, we have this oscillating structure for the theta when you increase this system size. So here, no matter how large the system size, infinite system size, we still have non-zero theta. Maybe on this maybe when you have some spatial n, this theta accidentally is 0. That's fine, but once you increase a little bit, it will become non-zero, right? This is a feature of this non-trivial Toeplitz braiding between upper angle and lower angle, right?
Just to make sure, for the upper angle, the L vector is 1, 0, 0, 0, and for the lower angle, it's 0, 0, 1.
Basically, you can try to use maybe 0, 1, 0, maybe 0, 1, 0, 0, and as long as you have some non-trivial and non-trivial Toeplitz between upper angle, you and lower angle, you can show this this vector properly because you have some complex unit cell with 2 layers, 3 layers. Yes, you are correct. The way we can choose 1, 0, or 0, 1, 0, 0, 0, 1, 0, as long as this non-zero component near boundary, near boundary, that's fine. That's okay.
Sorry. Yeah, so do you have condition on the type of the elements? I mean, for example, if for 2 elements in the same layer, if they have non-trivial braiding,
yeah,
then does it mean that they have non-trivial braiding?
You're right. So here I just this is a statement of existence. As long as I have some non-trivial non-trivial Toeplitz braiding. One way to do that, you just pick up the so-called simplest angle, like the 1/3 angle, 1/3 angle. That's fine. Because once you have non-trivial Toeplitz braiding between 1/3 angle, and then you can say that the braiding between 2/3 angle always here, right? So here you must try to find the solution. Okay, so now the direct question is that are there any symmetry requirements for this Toeplitz braiding? Because in topological incident and topological sequence, for the temporal wave classification, we need this strong requirement of symmetry. So do we need some global symmetry to protect this phenomenon? The answer is no. Because this gauge environment for tensor theory automatically guarantees integer quantized metric n into k. So as long as 3D box is not closed, it's open here. So this coefficient, this K is already quantized. As long as this box is gapped, right? So we don't need any additional global symmetry to protect this phenomenon. It's pure topological. We don't need additional chiral symmetry, whatever, also symmetry. We don't need any symmetry. Okay. Okay. If you insist on symmetry, we can say we have gauge symmetry to protect this thing, right? Although some people say that gauge symmetry is redundant, that's fine. so here we don't need some global symmetry over conventional definition to protect this thing. This is a very important point.
It seems that you need to have translation solutions each.
Yeah, no, yeah, you are right. So this is very important point. Maybe next time I want to add some additional defect to detect this. I don't know. This is very important in future development. In fact, it's very important future to add some additional violation of this translation part. So I don't know. So here the second question is why boundary zone mode lead to this Toeplitz breaking. So in other words, why the boundary zone mode of K matrix lead to this robust non-vanishing lower left and upper right of K inverse. This is pure mathematical thing, mathematical problem. So in the present with this quasi-zero mode, because we start with finite dimension, finite size, we don't have absolutely zero mode. It's only quasi-zero mode. This lambda 1, lambda 2 are two zero mode, which are quasi-zero mode. It's very small but finite because our dimension, the size is finite. Our starting point is finite. So in the present with this quasi-zero mode, this K inverse can be formally expressed in this way. The first two terms coming from this quasi-zero mode. This V1, V2 is bounding, anti-bounding wave function, and lambda 1, lambda 2 are corresponding quasi-zero mode, which is finite, but very small but finite. And once the system size becomes very large, we can have we can use this M matrix to give a very good approximation to this K inverse. We can forget about this third term, second term, etc. We only preserve the first two terms, this K inverse. Then we can use this matrix to give a very good approximation to this K inverse, because in general case we don't have this analytical way to solve this K inverse, right? K inverse is very hard problem. But in some special case, for this, when K is SSH Hamiltonian, we can compute this K inverse. But in general case, we don't have an analytical way to compute inverse any K matrix. So here we have a way to approximate this K inverse by using this M matrix. We just preserve the first two terms that are contributed by this quasi-zero mode. We find that in this approximation, the lower left and upper right vector elements successfully reproduce this exponentially enhanced lower left and upper right vector elements K inverse. So
what's the definition for quasi-zero?
Quasi-zero is like here you have V1, V2. The corresponding wave function gradually localized on the boundary when you increase the system size, because in general the system size is finite. When you increase the n, then this V1, V2 will localize on the boundary. So the corresponding eigenvalue, we call it as quasi-zero mode. Okay.
So the value of lambda 1, lambda 2 may not be very big.
It's finite.
Not very small.
It's very small, but it's finite. When you have finite n, but when you approach this n to infinite,
It really goes to zero.
Yeah, zero mode. Because we already said in the present, okay. Our starting point that assume that K has boundary element. But when you do this ED calculation, you have finite size system. There is no exact zero mode here. So right. So but it's a quasi mode is very small but finite. Once you approach this thermodynamics, we have this very good extrapolation to this absolute zero.
What's the relation between being exponentially localized on the boundary for the wave function and being very close to zero for the lambda?
Oh, I think these two things happen simultaneously. I don't have very good understanding for this thing, but
I think this requires some assumptions of the K matrix. For example, I add some identity to the K matrix.
Yeah.
It doesn't change the profiles of the wave functions, but the lambdas will change.
Yeah, but we may discuss later. But here what I want to say that we have this translation invariant K matrix. So this Toeplitz matrix. Once you increase this system size, you must preserve this translation symmetry. So this identity may be avoided.
It is translation invariant. That this identity is just a diagonal matrix with some, say, even entries.
Where you want it? So
yeah.
So here.
Yeah,
right?
it's just some diagonal matrix.
Diagonal matrix.
Yeah, with the same entry everywhere.
So here.
No, just a diagonal identity matrix.
Identity matrix.
I'm just adding some identity matrix to the image.
Yeah. This identity matrix may be regarded as an unsaid. Unsaid chemical rotation or something like that. But yeah, my understanding is that once you add this identity matrix and study this topological invariant this candidates in the context of topological integration. Once this topological invariant is non-zero, we can follow this result of the topological integration.
But the topological invariant of the topological bands is defined using the block wave functions, not using the spectrum.
Yeah. Yes, you are right. So here is some boundary correspondence. Once you have non-trivial topological invariant, we claim that there's some boundary level. This is the
but I think in general, there needs to be some additional condition to relate a small lambda to localized V.
Sorry, may I some answers our question?
Yeah.
And if you add some diagonal or some on-site potential to this SSA model, you just shift the whole spectrum to a constant. And it doesn't really change the eigen wave function.
Yeah.
And if you just apply the same transformation the inverse of that whole matrix, I don't think it will affect much. Because you can always subscript the on-site potential and it will not change the topology.
Maybe we need to redefine this zero energy. Is that right? Redefine zero.
Yeah, we can shift the whole spectrum to up to a constant.
Yeah.
But the interesting point is that lambda at that time might not be really small. Then how do you know that one more lambda really dominates the inverse? That may not be clear.
Yeah.
But I suppose the important point is not still necessary. And it's something we want to make this.
Yeah, I'm not sure here. Maybe we need to add some more condition, but I think
usually when we see localized modes have zero energy, that's already assuming the block container has some kind of particle symmetry.
particle hold.
Yeah.
Particle symmetry.
That's why the spectrum looks so symmetric. And if there's some modes localized, is localized in the middle. Otherwise, it can be shifted.
Yeah.
And in SSA model, zero mode is protected by the error symmetry, and it just kills the sigma y components, and the identity matrix will not affect the logical aspects of this model.
Yeah, that's right. So the topological aspects is determined by the wave functions, not by the spectrum. But here it seems we are making use of the smallest of lambda to approximate the entire K-inverse using the first two terms.
Yeah, here we just want to understand this asymptotic behavior of this matrix. Maybe we don't want to talk too much about this sort of thing. We just okay. We here want to try analytically to understand this asymptotic behavior finite size. Just some way to do the ED calculation.
If I understand correctly, this unconventional Toeplitz braiding actually can be boiled down to the diverging boundary components of this inverse matrix.
Yeah.
And I suppose that we have so many ways to do that in a 1D lattice system.
Yeah.
Like a
Yes. Yes.
We can always do that.
Yeah. As long as you have this canvas with non-zero boundary remote, we can use this this canvas to realize this Toeplitz braiding. We just follow this matrix from free function topology.
Yeah, I guess you are assuming that zero mode happens at the boundary. In general, the zero mode doesn't have to happen at the boundary.
So here we assume the boundary zero mode. Maybe you have bulk zero mode. Bulk zero mode. Okay, you're right. So here we assume the bulk is gap. If we interpret this K as harmonic, we have topological instrument.
And also the boundary mode may not, for the boundary mode lambda may not be zero. If I shift the entire K matrix as my.
Yeah, you're right. Maybe we need to design this K matrix very carefully. Here we really need this boundary zero mode. Maybe you have some very fine design for this K matrix. That's fine. So here we don't talk about this how to design this K matrix, but we are talking about this condition. We need this boundary zero mode. How to realize boundary zero mode? That is automated discussion.
Okay, another question is, we focus on the first two terms, and there are another two n minus 2 terms. When n is large, it's not clear to me that other terms are small.
Yeah. Okay. I'm physicist. Okay. I'm physicist. What are we allowed to answer your question? we assume they're small, right? We assume they're small because our numerical results they are small, so they are small, right? Satisfied? So we are not mathematicians, right? So we find okay, that's the boundary zero mode. There are two types. There are two zero modes and one zero mode. We find that in type 1 there's TI, TSI, but type 2 they are not present in TI, TSI, maybe are not physical in that context. That's fine. There's the mathematical result. So there's two boundary zero mode, one boundary zero mode. So in general, boundary. And here there are some numerical calculation of second, third, fourth example, because the first example is SS mode I already showed. So here's type 1, type 2, type 2. Here we find that this picture as the matrix elements plot of the K inverse. We find this all these examples are non-trivial, have this non-trivial Toeplitz braiding because this K inverse has non-trivial, non-zero lower left and upper right. Even the system size is bigger and bigger. So here we find that indeed this theta angle is oscillating when you increase the system size. This is numerical calculation, which is much more simple. So here this trivial one, the fifth example is trivial one. Once you have this A, this B forming the K matrix, we indeed have this distribution with the braiding phase angle are all localized along near this main diagonal. So this lower left and the upper right is blank. So we don't have a signal. So here the phase angle roughly goes to zero. Exponential decay. And because we can add additional symmetry charge here. So we can calculate the so-called charge fractionation of anion with each layer. So we found this when you have non-trivial Toeplitz braiding, the charge fractionation distribution of on the z direction are oscillating, randomly oscillating, and when you consider open boundary condition. But when you consider PDC, purely boundary condition, it's flat, some flat. And the same as the second example, the third example also shows a similar phenomenon like this. This two example also the same. But when you choose the fifth example, which has trivial Toeplitz braiding, and both OBC and PBC show the same result. When you put the system with open boundary condition along z direction, we don't have this random distribution, which means that open boundary and the pure boundary have the same result, have the similar for the distribution with charge fractionation. Here, so by definition, this charge fractionation is mode 1. We already mode is number one, because 1 is non-fractionized charge carried by electron or some trivial particle. So here I only have one or two slides. Here is on paper on progress. We put this we further starting 3D theory, 3D topological order along the fourth dimension. Now we expect that in some way we have some Toeplitz braiding between particle and loop. We put the particle in one boundary and loop on another boundary. This boundary is 3+1D boundary. The bulk is 4+1D. So now can we have some very strange particle loop braiding? Although when you braid the particle cannot see there is a loop. So this very strange particle loop braiding, this analog is very strange, highly analog. So because these particle loops are separated by this very large fork, 4-dimensional, 4+1D bulk. So can we have some similar story? Yes, this is very interesting that now if you use this BF theory, K matrix BF theory, now this Kij are allowed to be asymmetric. Now the popular direction, non-Hermitian physics. now we can borrow this very fruitful knowledge from non-Hermitian physics to study this strongly correlated PRD results. so here we found that we can use Fracton type or non-Hermitian SSA model to study this because it's non-progress. I just show some key result here. So instead of scheme modes, we don't need to compute scheme mode. Here we just do this SVD composition for this K matrix. We find that once you have the boundary labeled for this single bound decomposition, instead of ED diagonalization, we have this Toeplitz braiding. This Toeplitz is very strange between the particle loop. This particle is on this 3+1D universe loop on another 3+1D boundary. So it's parallel universe. They can feel each other, but they cannot see each other. They can feel each other in this topological experiment. Okay, this is some numerical result. We found this, and this is because now K can be asymmetric. So this K inverse is also asymmetric. So as long as either lower left or upper right are non-zero, they can support this Toeplitz braiding. As well as we add additional minor condition to avoid 2π, the trivial 2π, 4π, the 2π mod 0, right? So we add additional minor condition. We find that there is non-trivial Toeplitz braiding. This Toeplitz braiding is particle loop braiding between particle loop from different universe. Okay, this is summary outlook. Yeah, 1 hour. We define a new type of braiding, Toeplitz braiding as boundary phenomenon of Fracton topology order in 3D and 4D. We use the knowledge of free-forming topology illustrator and non-Hermitian physics to strongly correlate topology phases to reach this result, reach its conclusion. There maybe exists a very interesting boundary phenomenon in this new type of topology order. And for the future direction, maybe we can compute this entanglement scaling by cut along the z direction to study this entanglement between the two subdimensions. And also we can construct nice model inspired by Fracton composite formula. Flux attachment, we always add some energy penalty to enforce this flux particle bonding to reach its transformation. This is very scientific here to then we can use this use DMRG or quantum Monte Carlo to study this nice model. Okay, this is advertisement in my this is my current research in my group in Sun Yat-sen University. We have very diverse interest, even ADS-FT. Thanks for your attention. Welcome to visit us in Guangzhou, Canton.
And that's thank Professor for the very nice talk. Any further questions?
I kind of want to know that in this phenomena, to what extent can we understand this phenomena as kind of 1D physics? Because but you also mentioned that the XY direction is extended.
Yeah.
And already at the thermodynamic.
Yeah.
I mean, if I imagine the system, the XY direction is kind of shrinking to a very small size, and somehow it's effectively a 1D understanding, like the quantum states at the two ends are kind of entangled in some way. But here, is it possible to have such a picture?
Yeah, impossible, because we assume that there is already thermodynamical limit XY direction. We only borrow the mathematical result from topological and non-Hermitian physics. Actually, the physics between the two sides are completely different. We just follow this mathematical result, the K matrix, this Toeplitz matrix theory. I learned from Wikipedia.
From that perspective, that means when you increase the size along the z direction, do you have a good, at least in some sense, a good thermodynamic limit?
Yeah.
Seems no, because your braiding theta, braiding phase is not converge, right? Unless you pick up some.
You're right. Now the braiding phase is not converged to some fixed value. This is very feature of a non-liquid state. The system now the fractional population is non-liquid state. Non-liquid state. You don't have the very well-defined thermodynamics in a conventional calculation, because you see that Gauss density for this state matter are increased by increase this system size. Usually, like fractional Hall or conventional like 3D torical model, the GST is finite. Is a fixed value, no matter how large the system size. The value is fixed, is a fixed value. But here in the GST, when you increase the layer, the GST must be increased in the simple case. Maybe in some other case, maybe oscillating, maybe small, larger. So in this system, we usually call it non-liquid. Maybe my definition is different from.
But it's still a gap
phase. Because the low energy phase theory of this state is transforming theory. Transforming is gap.
That means the correlation functions two ends are
short-range correlation. The conventional correlation is short-range, but this braiding is entanglement theory, maybe. So this is the reason why I want to study the entanglement theory for this system. Maybe very interesting scaling, but I don't have a method to study from field theory way. I'm learning some paper by Edward Fracton, but still try to digest. That's very hard.
Maybe one comment related to your question. We can ask for the so-called upper and lower anions, what's the shape of their string operators? Normally, if we only consider one layer, the string operator will just be supported on this layer.
Yeah.
I think here the shape will be extended into the entire.
Yeah.
But if you recite two anions on the bottom and two anions on the upper top,
Yeah.
do they still finish such weird? If you have two anions decided together, somehow the ring-home operator is kind of localized. Not sure.
You can. I've noticed started this when young, but as far as I know, this is abelian topology. That's very simple. Every topological data is a simple structure and is sum, just add.
Okay.
But if you consider non-abelian, stacking non-abelian to non-abelian Chern-Simons theory to do that, that is very complicated but very interesting direction, beyond my capabilities.
So regarding the entanglement scaling, are you expecting something about this area law?
Error law should be there because it gapped, but maybe some subletting. Subletting will be affected by the Toeplitz braiding. This is my interest here. So I'm still working on, but it's very hard to compute entanglement entropy from this field theory and perspective because we need to do this replica. To study linear entropy, that's beyond my capability. So I asked my students to do that. So I try to learn. There's an original paper by Edward Fracton and maybe some other friends who it's very hard to read.
Any other questions?
I have a question regarding the SSH and the data model. And the only common point of this model is actually the exponentially decaying localized space. And can we extend the picture of the inverse of the effective one component to a more generalized case rather than to conceptually totally different models in 1D?
In 1D.
Yeah.
Here I only pick two examples, the SSH and
yeah, I think
many other examples. I only use this mathematical structure of this Toeplitz braiding. You can do the job to connect this mathematical structure to free-fermion. But here, even you can use this 3D topology with boundary Dirac cone. That's fine. But as long as you open one boundary condition, that's Hamiltonian still that's Toeplitz braiding. No matter how many dimensions you have in the site of a topological insulator, as long as you have one dimension or one boundary condition, open boundary condition, the other one is momentum space, then the Hamiltonian still Toeplitz braiding. Here, so we have some general result here. The requirement to have this two boundaries, but here we still assume that A and B are simple 2x2 matrix. You can 3x3. That's a very complicated thing, but beyond my capability, because we just want to pick up some simple example, demonstrate my physical result. That's fine because we are physicists. Maybe.
And if we add some more complicated boundary condition like the Mobius connection to the two boundaries, they say modified of this matrix.
Of course.
I suppose the inverse of that matrix will not differ to this scenery to a large extent.
Yeah, maybe only yeah, you are right. So I only have one paper to do that. Maybe we can do the next paper. And like this Mobius boundary condition. For our simple people, we start with open boundary condition to have a paper get published, and we have confidence. This doable. This direction is doable. Next we can add some additional talk. Additional talk. Is it appetite? Maybe it's appetite. We have some dessert. Maybe finally we have some dessert. Like the twist boundary condition, add flux, and confirm deconfirm phase transition over gauge field, add additional max return, blah blah. That's a lot of bunch of very interesting projects. Yeah.
Thank you.
Well, yeah, we'll be here for a week. You can talk to him later.
I only have knowledge of 1D topological models and non-mission physics, so I have no of good prior knowledge to this transform theory.
Well, that's as of today. Maybe after 1 week, you will become an expert in K-matrix. K-matrix is very simple.
Yeah, very simple. Yeah. I learned chemistry when I was undergraduate. Very simple. Yeah, I graduated in 2007.
Any further questions? Okay, if not, let's thank the professor. Thank you.